So, okay, so I thought I would, with maths, I'll sort of explain how we'll sort of do the sessions. So what I'll do is I'll sort of introduce either 1 or 2 or 3 new topics each time, go through the rules behind them, if there's any laws behind them, then go through a few examples, using exam questions as well, usually. And then if there's a couple of different methods we can use a couple of different methods. And then what I will do is I will send a set of questions over afterwards that relates to each new topic that we've looked at in maths. And then what my plan is that then by next week, what we can do is, if you then are able to get me the questions back over, I can look through them, and if there's then any errors or any areas where we maybe have a little bit of a misunderstanding, like the first 10-15 minutes of a session, I can talk through the answers. Obviously, if they're all perfect, then it's not too much of an issue, but yeah, talk through the answers, and then do a whole new section. So that's sort of the plan with this anyway, because it seems like the most sensible idea with maths. So I thought we would start with, if my pen would work, there we go, rearranging formula. So this is a skill that you'll have done loads at GCSE, but basically what happens is, what happens is we get to A level and we often haven't done anything for a while, and this is basically one of the skills that we sort of have to be able to do and use in all the different topics in A level maths. So A level maths is made up of core maths and statistics, and then in A2 there's some optional modules, but the first topic for core maths, which is one that you have to do before everything, is officially called solving problems. So we sort of will do a little bit of that today as well, and so we'll sort of bridge the gap between GCSE and A level. And rearranging formulae is one of the really most important ones for this. You'll need to do this loads of times. It's a topic where you'll have rearranged formulae before. It's actually a really nice topic to be doing as well if you're taking science A levels as well, because rearranging formulae properly is something that comes up a lot. And if we understand the logic of it, it's really, really useful. So yeah, we'll look at rearranging formulae. And we'll have a little talk about the first topic, which is problem solving, and then have a little look at indices. But yeah, this whole first topic of A-level maths is called problem solving, and it's all about, it sort of leads us on to being able to do proof, and I'll talk about sort of the ideas behind it. But the first topic really is all about having a really good sound way and method and building our methods of problem solving in maths, because at GCSE it's very much here's a question, here's the answer, and it is the same at A level, but now it's more, we have this whole section called problem solving where we're actually given a question where we have to sort of maybe use trial and error, where we maybe need to use different methods to try to get us to the answer. And it's not necessarily there's a set way to get there, but there is a set answer. So we'll look at that in a bit more detail in a little bit. So we'll start off with rearranging formulae. So I'm going to start off with an example. So what we are going to do is we are going to rearrange the following formula to make X the subject. So to make X the subject, what's really important is, like you were probably told lots and lots of times at GCSE, it's possibly even more important now at A level, is that we are showing all our workings out, because it's like a story. We're showing actually how we got there, and now you will not get all the marks if you just have an answer written. You need to clearly actually show your process and show what is happening between each step. So how you got from one part to another to another. So we're going to rearrange the following formula to make x the subject, and our following formula is y equals mx plus c. So we're going to start off with the first method. This is a method that you might have been taught during GCSEs. People get taught using lots of different methods, but we'll call this one method 1. So pop method 1 here. Basically, what we are doing here is we are going to use the principles of BIDMAS, but obviously in reverse, because we are changing around this equation. We are rearranging the formula. So we're going to use BIDMAS backwards. So we have Sam Dib. Best thing to do, it would help if I had wrote a B there and not a D. The first thing that I would suggest you always do when you're starting off these questions is actually just rewrite the original formula. It just means that we can sort of show this story a lot clearer, and it's really clear where you're starting from. If you just come in with the next step, it can be misconstrued as maybe you've read the question wrong, and if you eventually get to a wrong answer, but you've had some correct workings out in the process, obviously you'll get marks. But if we don't have that original start point, it can sort of be classed as, oh, did they really start from the right place? Have you read it wrong? So start off with writing y equals mx plus c. And our whole process of this is we want to make x our subject. So if we look through here, BIDMAS, we would deal with our brackets first. We're going through BIDMAS backwards, so we're going with Sam Dib. So we would do any subtractions first. We don't have any subtractions, but we do have an addition, and that is our plus c over here. So we want to get rid of our plus c. So what we're going to do is we're going to use inverse operations. So obviously our inverse operation of adding on c would be taking away c. So what we are going to do is we are going to take away c from both sides of the equation. This long process that you've seen before, minus c minus c. So we would end up with this. We would get y minus c, because we've taken c away from a y. We don't have a c over there already, so it's c away from y, so y minus c. C, take away c, is nothing, so we have mx. So y minus c equals mx. So then we look at the next part. Okay, we have multiplication, so that's our next part that we're going to get rid of to be able to get x on its own. So this time we are going to, we want to move m to the other side. So what we are going to do is we're going to divide by m to have x on its own, to make x the subject. So we're going to divide by m on both sides of the equation. So we have y minus c divided by m. Now, it's important to remember, this is occasionally where people trip up, that we are dividing this whole part here by m. Not just the y, not just the c. Y minus c is divided by m. So we're going to divide that by m, and that is going to equal x. So we would end up with the answer. So where x is our subject is x equals y minus c over m. And that is your usual process of doing this. Some people look at this in a slightly different way. So just give me 2 seconds. I'm just going to copy some of this over. Control-C. We're going to have a look at it using a different method. Nope, I'm not going to copy. Helpful. So let's just write the equation up again. We want x to be our subject. So we want x as subject, and our equation is y equals mx plus c. Now, another way we can look at it, and some people I find this really helpful, or we don't find it helpful at all, so it's up to you which method you'd rather use. Some people look at it as layers. and they look at the layers in the format of how we've made this equation together. So y equals mx plus c. So x is a subject that we want, and it's wrapped in these layers. We've done other things to this x to make it equal y. So x, when it's multiplied by m, plus c. So c is our outer layer. C is our outer layer, the part that we want to get rid of first. So actually, this ends up being very similar to what we started off with on the other method, but I'm just going to show it you as another example. So we're going to get rid of that outer layer. So we're going to get rid of that plus c. Obviously, we're going to use the inverse operation. So we're going to minus c from both sides. So you end up with y minus c equals mx. And then we want to get rid of our next layer. Next layer, quite simple. We can see here it's m. So m has been multiplied. So we want to divide both sides by m. Obviously, this is exactly the same as the one before, but I'll show you another one in a minute where it does differently. So we would have y minus c divided by m equals x. So we'd have the same answer. Some people prefer this method because they can see the layers easier than using BIDMAS backwards. It just depends on what you prefer. So I'm going to give you a different example. This is from an A-level paper, this question. We are going to make T the subject of the formula. Remember, we're going to show all our workings out because it's like a story. We're showing each process. So our equation, this is one that will come across a lot in physics. So S equals half AT squared. And I'm going to show you both methods again. So we're going to start off with your usual method, which is using BIDMAS backwards. So we'll go SAMDIB. Okay, I'm just going to show you some annotations and shorthand that we start to use a lot in maths. Because I'm saying we're sort of showing a story, we would say we don't want to use equals before we get to our final answer, because equals is our final, this number equals that. So we have this, it's an equal sign with an arrow. This means implies that. You may have seen it before. And also your three little dots, therefore. And you'll see me starting to use them as I'm working through the answers, because it makes it clear for this story. Oh, if we do this, this implies that, and this implies that. So what it sort of does is, so for example, when I did this method, I didn't need to show implies that, because I am showing you that I am minusing C. So I've got each step, I'm showing the workings. What would have been helpful in this one is if I hadn't got these minus C's bits here, I would add on implies that, but I'll show you that in a second. But we'll go through method one first. So we're going to use SAMDIB backwards. So we would start by rewriting the equation. S equals half AT squared. Okay, so we look at that. Have we got any subtraction? No. Have we got any addition? No. Have we got multiplication? Yes, we have got this half. Now we know that the inverse operation of multiplication is division, but we've got a half here. We're timesing by a half. Therefore, we know that timesing by 2 is the opposite of timesing by a half. So we're going to do that. We're going to times by 2 on both sides of our equation to start off with. So we're going to do times by 2, times by 2. So we're going to get 2s on this side. S times by 2 gives us 2s. Half times by 2 equals our 1. So what we're going to do is we are going to put 2 we're going to put AT squared on here because we've got rid of that half. Then we look at the next part. Okay, so we've done addition, subtraction, addition, multiplication. Oh yeah, we've got another multiplication. We've got A. So let's deal with A. A is a bit easier to deal with. Inverse operation of times by A is dividing by A. So we're just going to divide by A on both sides of the equation. So we will have 2s. 2s divided by A is 2s over A equals t squared. That now leaves us with our indices to deal with, our power. So we are going to do the inverse operation of to the power of 2, the inverse operation of squaring. So the inverse operation of squaring is the square root. Now, at A level, we don't just do square root. We have a plus minus sign here. I'm just going to add it on this side. This is because our answer can be positive or it could be a negative number, but square rooting it we can have either option. So what we do to make this a bit clearer at the moment is we put a plus minus next to our square root because it allows for actually, it could be this answer if we square root it with a positive number, it could be this answer if it was a negative number. So if we square root 2s over A, we get 2s over A square root. Remember your plus minus sign, and this would equal t. And that is our process for using the SAMDIB backwards. Now I'm going to show you the next method for doing exactly the same one, but just using a different method. So we'll write out the equation again. We've got s equals 1/2 at squared. We want t to be the subject of this equation. So we're going to make t is going to become the subject. So first of all, rewrite the equation. Let's start in the middle this time. So we've got s equals 1/2 over at squared. We want to remove those layers, okay? So we want to remove that half again. Like we've said, timesing by a half, the opposite, the inverse of timesing by a half is multiplying by 2. So let's use that implies sign. So let's put that implies in. This implies that 2s equals at squared. We've not done anything different to the method before, but we've added this implies in because what we're doing here is we're saying, we're not showing those lines coming down going, oh, we've divided by this, we've times by this, we've multiplied by this. Got rid of that and we just put, going from here to here implies that this has happened. Okay. Working through those outer layers again, we've got at squared. We want t on its own, so next layer is a. So we're going to have implies that. So we'll end up with, we want the inverse of multiplying by a, which is dividing by a. So we'll have 2s over a equals t squared. Then we need to get rid of the squared, so we're going to square root. So plus minus 2s over a equals t. So finally we need to make t the subject. So this implies that t equals plus minus 2s over a. So that was our second example. I'm going to show you a third example of rearranging a formula. So the final example, again, this is another question that has come from an A-level maths paper. So these aren't GCSE questions, these are from A-level questions. We're going to make, what are we going to make? I haven't written this fully down. We're going to make X our subject of our formula. I wrote down my plan, but I haven't written down. Yes, we are. We're going to make X the subject of the equation. X the subject of the equation. So, equation here is y equals x plus 3 over x minus 2. These are the typical questions where lots of errors can come in, because our biggest issue here is we have got x is in 2 places. So x is in 2 places. This is where the first big error can come in. This is where that word cancelling out comes in, and somebody goes, oh yeah, what I can do is I've got an x here, I've got an x here, so I could just cancel them out. So y equals 3 over minus 2. It isn't true, okay? We cannot cancel x. So if we go back, get rid of them before it stays like that. So in this situation, we can't cancel x. And we can't cancel x because the whole logic behind this is that they need to be on the same level. So if we've got x plus 3 divided by x minus 2, they are not the same. We've got them as a numerator and a denominator, so they are not on the same side. They are not on the same level, so we can't cancel them out. So we have to instead make sure that we're getting them all to the same area and making x the subject of the equation. So we cannot cancel x out to start off with. So let's have a look at what we're going to do first. So we have got x plus 3 over x minus 2 equals y. Let's get rid of this denominator straight away. Let's move this over to this side so that it's easy to deal with. So we've got just one line of equation. If we have divided x plus 3 by x minus 2, that means the inverse of this would be multiplying both sides of the equation by x minus 2, the whole part of x minus 2. So we'll pop our implies in again. So we will have y x minus 2. So y times x minus 2 equals x plus 3. So we have multiplied both sides of the equation by x minus 2. Now what we're going to do is we're going to get rid of those brackets. We don't want to deal with those brackets. Those brackets are messy. They make it hard for us to deal with. So let's expand those brackets like we would normally. So y times x would give us yx or xy, doesn't matter which way around you put them. And then y times 2 will give us 2y. So yx minus 2y equals x plus 3. So this is nicer to deal with. We've got rid of those brackets. It's a lot clearer to see. Right. We want x on its own, but actually we need all the x's on the same side of the equation now to try and make them a subject, because otherwise we're just dealing with them separately. So we actually want at the minute to have 3 on its own. We almost want 3 to be the subject. So we're going to remove this x here. So at the moment we have plus x. We've got a positive x. So to rearrange this formula, we want to do the inverse and we want to take away x. So what we should then get, if we take away x from both sides of the equation, is yx minus 2y minus x equals 3. Bit easier, bit nicer. So we're bunching all these x's together now. So we've got 3 on its own. Let's get 2y over to this side. So that is our new plan. We want to move 2y to the other side. We want to get x on its own. So let's move 2y. So we've got minus 2y here. Let me get my pen to work. This is minus 2y. Our inverse of minus 2y is plus 2y. So we're going to do plus 2y on both sides. So we'll have yx minus x equals 3 plus 2y. Now, it's not the last stage, but the next thing that we want to move is our y here. So we have yx. So we have y times by x we're going to want to divide by y. This time, so divide both sides by y. So if we divide first side by y, we have, oops, we will end up with x minus x. This side, we're going to divide by y, so we're going to have 3 plus 2y over y. Okay. It doesn't just stay as y on its own, and I'm going to explain this now. So x minus x equates to 1. So what we are going to do is we're going to remove 1 from both sides. So we're going to have x equals 3 plus 2y over y minus 1. And that would get you to your answer. So that would be our answer to make x the subject of the equation. So that is possibly the trickiest because we have x in 2 places. What we'll have a little look at now is this whole idea of problem solving. So rearranging formula is really important because actually we can use it for problem solving a lot. It's really, really useful when we're problem solving. And when you're given a question, if you know an equation, we know a formula, we know some numbers that we can fit in, if we can rearrange that formula, then we might be able to get to an answer. So we have something called the problem solving cycle. Solving cycle. So this problem solving cycle has 4 stages, and we sort of go around the whole stages as we go. And this is sort of a new concept that we're going to start using and thinking about as we're going through mathematical problems and mathematical problems to solve. So the first stage in the problem solving cycle is this. We get a problem specification and we're going to analyze it. So we find out what the problem is. We're going to analyze what that problem is, have a look at how we might be able to solve it, an analysis. So problems, we're going to look at it. We're going to formulate our problem at this point. We're going to find out what it is. We're going to analyze it. We're going to plan how we're going to tackle this problem. And we might actually collect information at this point. So we're going to find out what our problem is and sort of work out how we're going to plan it. We would then go to our second stage, which is information collection. Now, I did say that we could do information collection in stage 1, and it's a little bit of a different information collection. So depending on what your problem is that you've been given, you might need to collect information before to help you plan and then get a bit more information again. So we'd collect information for stage 2. So we collect data or we carry out an experiment. In an exam, you might just be given this data. So you're actually going to sort of do 1, then be given 2, and then you go on to stage 3. So stage 3 is processing and representation. And what happens here is you're going to use mathematical techniques to make sense of the information you're given. So we've worked out what our problem is. We've sort of made ourselves a plan on how we're going to solve this problem. We've got some data. We're now going to process our problem. So we're going to use mathematical techniques to make sense of the information. We're going to represent it. And then finally, our last stage is interpretation. Now, we've called this a cycle and explain why it is a cycle in a second. So we have interpretation. So interpretation is we've got these results now. What does this mean? And actually, we're problem solving. So we get to the interpretation stage and we might go, oh, hang on. No, this isn't the right answer. And then we go back again and we adjust our plan and we adjust the process, we adjust the method as we keep going. Trial and error does come into this, strangely enough, and I'm going to give you an example that is often used for the problem solving cycle. So for example, you could be told that you will be given some specifications. So it's the Olympic Games, and you've been given the specifications that every team must play a minimum, so we'll put minimum of 3 games. So every team has to play a minimum of 3 games. And your winner is going to play 7 matches. So every team has to have a minimum of 3 games that they've played. The winner has to have played exactly 7 matches. Okay, so they're your specifications. They are what your problem, your answer to your problem is going to have to fit. It's going to have to fit into these. We've got 3 games, minimum of 3 games. So we're going to have enough teams. We've got a minimum of 3 games, and the winner's going to play at least exactly 7 matches. So your variables, what you've got to work out then is, let me change that to that one, is straight away the number of teams. So how many number of teams are you going to have that allows your winner to have specifically played 7 matches? So your number of teams, your number of groups, as in quarterfinals, semi-finals, finals, how many group stages is there going to be? And then we need to know the number that are going to qualify from each group. And this is where, oops, we would use this stage. So we would come up with our problem specification analysis. And then we would sort of process this information, sort of go, okay, so what is some logic here? So we're going, okay, so we've got a minimum of 3 games. So the winner's got to play at least 7 matches. So you would work this backwards. So let's say our winner is Team W, and they're going to have to play at least 7 matches. They're going to play against Team L, who are the losing team, and they're going to have played 7 matches as well. For them to have come face to face, we know that they will have had to have played another team to get there. So both of them will have had to have played. So let's say W played Team A. So this was W's 6th game, and L played Team B. So that was their 6th game each. Actually, for each of them to have got there, they will have had to have played other teams. And this is the process then that we start to work out, is who's played with who to get there. So let's clear that. Let's make this a bit clearer. So W is our winning team. Put a circle around them because they're the ones who end up winning, but they play with L. And this is their 7th game. It's the final match. So we've gone through 7 games. Doesn't mean there has to be 7 stages. So that's another thing that you can start to think of. Okay, it doesn't mean there has to be 7 stages. It just means that I have to have played 7 games. So that means they've at least at some point both won against each other through the processes. So you can see now that you can start to make out a plan and execute that plan using mathematical reasoning and logic to get there. So you can use algebra, you can use lots and lots of different other methods to get there. And what we're going to do is we're just going to split this up slightly by looking at, if I can find where I've put it, a different problem. So bear with me 2 seconds. I just need to find where I put words for this problem. Here we go. Sorry about this. I'm just trying to work out where I've just put the questions, and I've done my whole method and I haven't actually written down the questions. Here we go. So problem solving, logic behind it. So you get told a rectangle has a length, and let me get this up actually, this will be more helpful. Has my whiteboard gone? So we get told Hi.
I sorry, it just got disconnected.
It's fine, don't worry.
Yeah.
So yeah, I'll just pick up where we got to.
No.
So yeah, so what we get to now is we'll look at an example for problem solving. So if you are told, for example, a rectangle has a length of x, and dogs, stop, and a width which is 3 less than x, you're then asked to come up with an expression that represents its area. So this is quite a nice question, really. So you need to come up with a expression that represents its area, So obviously we know to work out area, we can remember that the equation is, right, you two, stop it. We can remember that it is length times by width. So length times by width will give us the area, and it's area squared. So now tell us what our area is. So you can actually just draw this out. Obviously, you've probably worked this out already, but we can work it out through drawing out. This is the problem solving aspect of it. So we go, okay, so rectangle has a length of x, and it has a width 3 less than x, so that will be x minus 3. So what would this look like if we wrote it out? Well, we know that it's going to be x, and we're going to multiply x by x minus 3. So this would be our expression, and it's as simple as that. Our expression is x times by x minus 3. And that would be our expression for our rectangle that has a length of x and its width is 3 less than x. I'm going to go through another example with you now. So Beth and Polly, these are the sort of ones that we use quite a lot. So Beth and Polly are twin sisters. So we've got Beth and Polly, and they are twin sisters. So Beth and Polly are twin sisters, and their sister Louise is 2 years older than them. Their total age is 32. Oh, that looks like 52. So let's rewrite that so it actually looks like 32. So their total age is 32, and it wants us to come up with what are the ages of the 3 girls? What are their separate ages? So we can look at this and go, okay, well, let's define Beth and Polly's age as x. So we're going to input algebra to use algebra to be able to problem solve this equation. So okay, so Beth and Polly are x years old. So they are both x years old. So we're happy with that. So we've got Beth who's x years old, we've got Polly who's x years old, and we've got Louise is x years old plus 2 years on top of that. We go, all right, okay, so we've got x plus x plus x plus 2. That must mean that they are, 3x plus 2. So that is their age, 3x plus 2. So we can look at it and go, okay, so we've got 32. So we know that 3x plus 2 equals 32. So we can use some of our rearranging equation again to work out where we are. So actually, let's start off. Let's get rid of 2. Because we want to work out what x is. At this point, we want to work out what x is. So let's get rid of the 2. So we're going to take away our 2 from both sides of the equation. So we would have 3x equals 30. Okay, so 3 lots of x equals 30. We know then that x must equal 10. So therefore, the ages of the sisters are 10, 10, and then left over with the 2 with the 10, 12. So that's that problem solving process behind it again. And I'm going to go with one more, just sort of talk you through the problem solving aspect again. So we have somebody called, they really like these to be sort of those wordy sort of potential questions. So we have someone called Anya. And Anya has 400 meters to create a fencing to create a paddock for some ponies. So she's got 400 meters to create a paddock. She wants the paddock to be twice as long. So the paddock is going to be twice as long as it is wide, twice as long as it is wide. We need to calculate what the area of the paddock will be. So again, we're just going to apply our algebra to this. So we're going to draw out our paddock. This is where the problem solving and the trying things again and again and again really does help. So draw our paddock out. So it's going to be twice as long as it is wide. So wide, it's going to be x. Twice as long, it's going to be 2x. So the area would be 2x multiplied by x. So we would have 2x squared would be our area. So then we need to look at it and go, okay, so how do we break this down then into 400 meters? So let's draw on all the sides. How many times does x appear on here? And it would be the most logical way to sort of go with it. And we go, okay, right, so 2x squared gives us 400 meters in total. So we've got x once, 2, 3 times, 4, 5, 6. We've got x 6 times. So this 400 is going to be divided by x, divided by 6 equally each time. So we would have 400. We would divide it by 6, and that would equal 66.666 reoccurring. What we are then going to do with that is we know that is our perimeter. So we're going to then times this. So we're going to times this by 2. So we would end up with 8,890 meters per square. Meter squared, sorry. And so the logic behind this is that is our area, because we've just worked out our dimensions of our perimeter. And once we've got our dimensions of our perimeter, we are then going to multiply. That would help if I'd put that in here, them together. So if I talk this through again, the paddock is 400, has a perimeter of 400 meters. We've applied the algebra to represent the length being twice as long as our width. We've represented it with being x. We've got 6 lots of x in this equation. So we go, okay, perimeter is 400. We need to actually work out the length of each side. So if we do 400 and divide it by 6, that will give us 66.666 recurring. So if we then get 66.666 recurring, times it by 2 to that, because that is our length of one width. So one width over here is 66.666 recurring. Our length would be 2 times 66.666 recurring. Multiply them together for our area, and we get 8,890 meters meters per squared per meters. I don't know what's happening with my words now. That is the process that would happen for problem solving. Another thing that comes up with problem solving, and this is sort of bridging topic again, so sort of bouncing back to bridging topics, is indices. And there's obviously lots of laws of indices. So we're just going to talk through a couple. and look at what happens. So if we have, this is when we're going to simplify. You'll ask, simplify this, simplify that, and we have indices involved. So if we have xa multiplied by x to the power of b, you would get x, and we would have a plus b. Now, what you cannot do is you cannot just add your two indices together at the top if your base numbers are different. So by that, I mean, if we had ya times by yb, no, yb would work, ya times by xb, we can't just add them together because we would actually have yx and we have the a and b, we can't just add them together. So our base numbers have to be the same. So I'm going to show you this actually with some actual numbers involved. So if we had 2 to the power of 3, and we are going to multiply it by 2 to the power of 5, we are going to get 2, I'm going to go to the power of 8. This is the correct answer. What often comes up is something that looks a bit more like this. So you get 2 to the power of 3 multiplied by 2 to the power of 5, and then somebody writes 4 to the power of 8. That's not what's happening here. So 2 times 2, yes, does give us 4. But if we write this out in long form, we would actually have 2 to the power of 3. So we've got 2 times 2 times 2 to the power of 5 times 2 times 2 times 2 times 2 times 2. I think I wrote that enough times. 1, 2, 3, 4, 5, 6, 7, 8. We've got it 8 times. So that equals 2 to the power of 8. It doesn't equal 4 to the power of 8 because we're not multiplying those two separately. They are base numbers that are the same. So our base number remains the same. We're just adding on our indices, how many powers, how many times we're times in 2 by itself. So it's 2 to the power of 8. So that is our first rule for our indices. Yes, we can add those indices up, add them together, only if our base numbers are the same. So we've got the same base number, and also we don't multiply those base numbers together. We don't multiply those base numbers together. So let's have a look then at indices if we are going to divide them. So we have got number 2. Let's go with xa again. So xa is divided by xb. So our base numbers are the same. We still have to have the same base numbers. The same rules when we're doing multiplication. We need to have the same base numbers. So our base numbers are, base numbers are the same. So this is nice and easy because our base numbers are both the same. When it was multiplication, we added our indices together. Now it's division. We're going to take them away. We're going to subtract them from each other. So we would get x equals x to the power of a minus b. Again, if we had, let's pop a number in. So let's use the numbers from before. So we have 2 to the power of 3, and we're going to divide it by 2 to the power of 5. We're not dividing 2 by 2. 2 stays the same. So we put our 2 here. 3, take away 5, give us minus 2. So 2 to the power of minus 2. We do this because our base numbers are the same. We're taking those two numbers away from each other. Let's look at one that's not necessarily more complicated, but one that creates a few more issues for people. So if you're given this, we have x to the power of a. So xa, x to the power of a to the power of b. So everything inside that bracket is to the power of b. Okay. This is where some issues start to arise. What it equals is x, ab. So x to the power of a times by the power of b. So let's talk through an example. Let's get this one up. We've got 4x squared to the power of 3. So let's expand these brackets like we would do normally. Okay, so we would have, there's two ways of doing this actually, but we'll go this way first. So we go, okay, so 4x squared, I'm going to get 64x to the power of 6. So I'm going to show you a different way that we could work this out. So we can then go, okay, let's expand these brackets. So 4 to the power of 3. And then we're going to do x squared because they come together to the power of 3. So we'll do 4 to the power of 3 multiplied by x squared to the power of 3. So 4 to the power of 3 will give us 64 x squared to the power of 3. Well, we can just do 2 times 3. 2 multiplied by 3 gives us 6. So we have 64x to the power of 6. So that's sort of the basics of where we would go with that one. It's 5 minutes, so I'll show you one more example using this one because this is where it gets a little bit sort of sticky. So I'll then do a bit more indices tomorrow. So let's use this one as an example. So we've got 4x to the power of 5, 4x power of 5y, all to the power of 3 over, over 2xy squared times by 8x power of 10 y to the power of 4. Okay, something like this, we don't want to have to try and tackle the whole thing together in one go. Deal with one bracket at a time. So let's deal with the numerators first. So let's deal with up here. So let's look at that on its own. So we have got 4x to the power of 5y3. Okay, so we're going to just expand everything like we did before. So we've got 4x to the power of 5. So 4 to the power of 3, like we said before, is 64. So we're just going to write 64 here. And then we've got x to the power of 5 to the power of 3. We're going to multiply 5 by 3, which will give us 15. So that gives us x15. And then y to the power of 3 gives us y3. So that'll be our first part. Then let's look at our denominators. Let's look at our bottom half. So we have got 2xy squared times by 8x10y4. I'm just going to deal with these like we would normally. So again, 2 times 8 gives us 16. X times by x to the power of 10 will give us x11. Y squared multiplied by y to the power of 4 will give us y6 because we're just adding those two together because they are both just to the powers. So this is where we get our therefores coming in. Therefore, from what we've worked out here and here, we will have 64x to the power of 15 y3 divided by 16x power of 11 y6. Now we can simplify this even further. So, okay, 64 divided by 16 will give us 4. x15 divided by x11, well, we've said that dividing indices together, we're just taking them away. So 15 take away 11 would give us 4. So we've got 4x to the power of 4. And then we have for y, so we're just going to take 3 take 6 away from 3, which will give us -3. So we have 4x to the power 4, y minus 3. And that is what we would do with a more complicated indices question. What we will look at tomorrow is fractional indices with powers and roots. Have a little look at surds, and then a little bit more of the problem solving. So what I will do is I will pop this video up on YouTube for you to follow and have a watch